scientific process as a unifying thread to make connections in chemistry. Yes, to make connections. What is its significance? To quote Donna Jo Napoli, an American linguist and young adult fiction writer, learning is not the accumulation of knowledge, but rather one thing only: understanding. It is all about understanding. And in turn, the operational definition of understanding is simply making a proper connection in one's brain between an incoming new information in the class or from the textbook and the already present old information. Thus, learning is all about one and one thing only, namely making connections. Let me illustrate this important idea using an analogy. Imagine different sets of links in the form of complex chains. Each link represents one information and each chain represents a set of related information connected together in the brain. Let us say a student in a class hears a particular information mentioned by the teacher or professor. If the student is able to find a suitable chain in the brain and connects the incoming link to a particular link in that chain, then the reaction is, "Oh, I see, I understand." On the contrary, if he or she is unable to connect the incoming link because there is a missing link or there are some missing links between the incoming information and a related already present one, then the reaction is, I am lost. The above role is played by neurons in the brain which can connect together and form neural networks. There are 100 billion neurons in a human brain. They are electrically excitable cells. On the average, each neuron makes 7,000 synaptic connections to the others. Use it or lose it happens to be the motto of the brain. Connections used regularly become stronger and more complex, whereas those not used get eliminated by a process called pruning. But notice that the first essential step is always making the connections. Thus, making connections is extremely important for understanding new information, retaining it in the long-term memory, and recalling it at any desired time in the future. Hence, the significance of making connections. If a student is thorough with the various results of the major activities of the scientific process that I discuss in this video and forms a chain of links out of them in the brain, that chain can play the role of a powerful, efficient, and effective unifying thread to which any student can connect all the information in the chemistry textbook as well as discussed by the teacher or professor in the class. This is illustrated here using the analogy of chain of links. The various info to be learned and mastered in the course can be effectively connected to the chain formed by the results of the scientific process. So, what is this scientific process? From an academic standpoint, it consists of four major activities that scientists engage in all the time, then the corresponding tools used by them, and finally the corresponding results, which happen to be 11 in number, as we will see. It is these 11 results of such activities that constitute the unifying thread mentioned earlier here. But before going into those details, at the very outset, I want to repeat what I just said on the previous slide in order to emphasize that this whole approach is purely from an academic point of view. In other words, it might be very useful to both the learning and teaching communities, and it does not refer to any of the research methods that the scientists adopt. It is simply concerned with how the constantly verified and hence established results of scientific research are processed in an effective and efficient way, since it is the results of such processing that find themselves in textbooks, which the students are expected to master. I am sharing this simply because all my serious students, who were very large in number, found it extremely beneficial for their understanding chemistry thoroughly by making proper connections effectively and remembering all the essentials efficiently. Incidentally, I am now retired. Soon after every semester began, the term missing links became a popular one among my students. They would start using it freely and frequently. Whenever they came to my office with questions, they would request me to provide the missing links, which would help them make the connections and understand. I would like all other serious students out there dying to understand chemistry to develop an extremely valuable perspective by watching this video. Those who are deep into philosophy of science may or may not agree with this approach. I totally respect their view, although the well-respected great scientist and teacher Richard Feynman happened to say, what science is not what the philosophers have said it is, in April 1966 in the 14th convention of the National Science Teachers Association during his lecture on what is science. In his lectures on physics on pages 2 through 7, he also said philosophers say a great deal about what is absolutely necessary for science, and it is always, so far as one can see, rather naive and probably wrong. The order in which the major activities of the scientific process are listed in this video series does not necessarily indicate a strict order in which these activities actually take place. Although modern science always considers major activity 1, namely gaining knowledge, as an essential first step. In the case of a natural science such as chemistry, this crucial starting point is gaining knowledge of nature, namely its properties and behaviors. The initial tool for gaining or accumulating knowledge happens to be making casual observations on nature. Some important casual observations led to the birth of the special branch of science that we call chemistry. They also resulted in the coining of a fundamental special term in chemistry, namely chemical change, also referred to as chemical reaction, which is the major focus of chemistry. They are listed here. The casual observations always prompt experimental observations, namely observations made on a specific chosen part of nature referred to as a system in a carefully and intentionally designed environment. The result of a desire to make this second kind of observation is what is called an experiment. That is, experimental observations are always made while performing experiments during which specific measurements take place with the help of a measurement tool or apparatus or instrument using a particular measurement technique. Scientists make this kind of observations constantly by performing experimental research and publishing the results in peer-reviewed journals for others to see. Occasionally, during such research, totally unexpected third kind of observations called accidental observations happen to be made. A breakthrough in science in terms of radioactivity was due to such an accidental observation. The result of any of these three kinds of observations on a given system in nature is an isolated fact. A fact is a statement that summarizes what has been observed. The published results of research are constantly verified and established, and those that do not succeed such verification are dumped. Only the established facts find themselves in textbooks. The precision associated with the measurements is also continually improved whenever technology makes it possible. Chemistry has accumulated millions and millions of loose, isolated facts on nature through various observations. The major activity of accumulating facts about nature is still going on in chemistry and will continue to go on. The facts resulting from those observations can be either qualitative or quantitative. A qualitative fact has no numbers at all in its statement, while the quantitative one has at least one number in it. A couple of examples of qualitative facts are listed here. Notice the absence of any number in these statements that summarize what have been observed in nature. And a couple of examples of quantitative facts are listed here. Notice the presence of at least one number in these statements that summarize what have been observed in nature. In the absence of the second major activity, we would have to deal with millions of isolated, loose, individual facts. This activity's objective is to avoid it by generalizing and organizing them whenever possible, looking for and recognizing some or other commonality present among individual all related facts is a major activity of science. There are two different tools used for generalizing or organizing gained knowledge about nature. The first one is comparing and contrasting on some particular basis or set of bases, a set of related facts, and recognizing the existence of similarities and differences among them. This results in empirical classifications in nature. Classifications are extremely powerful. To understand their power, all that one has to do is just imagine walking into, for example, a grocery store where the items have not been arranged in a classified manner at all into, say, produces, dairy products, meat items, cosmetics, pharmacy items, etc. But placed in a random fashion, and you are having to find a specific item that you need urgently. Again, every scientific classification is characterized by a unique basis or a unique set of bases on which the comparison and contrast are made. When a student learns about any classification, it is important to pay special attention to the basis or the set of bases on which the given facts are compared and contrasted. The basis or the set of bases used is unique to each given classification. Once that basis or the set of bases of comparison and contrast changes, the very classification changes also. For example, matter happens to be classified in different ways using different bases. The physical classification of matter into solids, liquids, and gases is the result of using size and shape as the basis for comparing and contrasting the corresponding facts as shown in this table. The terms solid, liquid, and gas are common nouns coined specifically to refer to each member of this classification scheme. Each is defined in terms of the corresponding similarities and differences. For example, a liquid is a form of matter that has a fixed size independent of the container it is in, but a variable shape depending on that of its container. On the other hand, a solid is a form of matter that has both fixed size and shape, which are independent of its container, while a gas has neither fixed size nor fixed shape, both of which depend on its container. Each classification scheme in turn leads to its own corresponding common nouns for its members. On the other hand, the simple chemical classification of matter into substances and mixtures is the result of using purity as the basis for comparing and contrasting the corresponding facts. A substance is 100% pure while a mixture is not. It is important to keep in mind that in practice, it may be impossible to obtain a substance as 100% pure. In reality, it might be just 98% or 99.9% pure, yet it is a substance. And the extended chemical classification of matter into elements, compounds, and mixtures is the result of using separability, identity, and composition as the basis for comparing and contrasting the corresponding facts as shown in this table. Given the commonality for elements and compounds with respect to both identity and composition, they both qualify to be called substances as opposed to mixtures. That is, one should imagine any element or compound as 100% pure, irrespective of our actual ability to obtain it that way. In this sense, substance is more of an idea than a fact. Chemists have taken this approach because it has been found to be very useful to discuss chemistry. In anticipation of what we will discuss in major activity 3, let me point out here that when a chemist says, for example, copper, which is an element, he or she imagines in mind a very large collection of just copper atoms only without any other kind of particles being present. To a chemist, water, which is a molecular compound, refers to a very large collection of just water molecules only without any other kind of particles being present. Similarly, sodium chloride, which is an ionic compound, means just a very large collection of sodium chloride formula units only, where each unit is made up of one sodium cation and one chloride anion. No other kind of particles is present in that collection. This has the immense power of making our discussion of chemistry extremely efficient. This empirical classification is at the heart of chemistry, which is basically a study of about 100 or so elements seen in the most powerful empirical classification called the periodic table. The millions of compounds such as water, table salt, sugar, etc. formed by the chemical combination of elements and a large number of mixtures of elements alone such as brass and bronze, or of compounds alone such as saline solution, or of elements and compounds such as air. Some other examples of empirical classifications in chemistry are listed here. Several of these have more than one set of bases, yielding different classification schemes and the corresponding members. For the corresponding bases and the resulting members of the classifications, see my book Understanding Chemistry. In general, textbooks of chemistry do not address the basis of empirical classifications. In fact, they do not refer to this important aspect of classification at all. It is essential that they do so, and I hope this trend will develop in the future. In part 2, we will discuss the second tool used in major activity 2A and also look in detail into major activity 2B.